Hello everyone, welcome to quick revision series of strength of materials. In this video, I will be discussing about bending stress theory. First, we will be seeing what are the assumptions in bending stress theory. Next, what is bending stress equation and what is section modulus, and some details in section modulus. Now, coming to the assumptions in bending theory, first assumption is material is isotropic, homogeneous and elastic. In brief, let's know what is homogeneous and isotropic material. Homogeneous material is nothing but the material which has same properties in a particular direction at every point. Whereas isotropic material is nothing but if we consider a particular point in a material, at every direction it has same properties. Like at this particular point, at every direction it has same property. Okay. Now, what is elastic? Elastic is nothing but loading is within the elastic limit of the material. Here in this case, Hooke's law is followed by the material, that is stress is Young's modulus into strain is followed. Coming to the second assumption, material is equally strong in tension and in compression. Third assumption is cross section is symmetric in the plane of loading. This is nothing but we will be taking a prismatic cross section. The next assumption is each layer of the beam is free to expand or contract independently. If we take a beam, after bending action, it bends something like this. If this is the neutral plane, above the neutral plane, all the layers will be subjected to contraction, and below the neutral plane, all the layers will be expanding. At the neutral plane, there won't be any expansion or contraction. The next assumption is the plane section before bending remains plane after bending. But this assumption is nothing but it is indicating the strain variation is linear throughout the cross section with 0 at neutral axis and maximum at top and bottom layers. For this assumption to be valid, that is plane section remaining plane before and after bending, the beam must be in pure bending. Pure bending is nothing but the material should be subjected to only bending moment and there should not be any shear force acting. Now, let's see how plane section looks before and after bending in case of pure bending case. Here, pure bending is nothing but we have seen that it should not have any shear force acting. There should be only bending moment. Here, if we observe, there are two moments on this beam acting, and this moment is creating a sag in this beam. Because of this bending, because of these two bending moments, the beam bends something like this. Here if we observe, there is compression in the top layer and tension in the bottom layer. Because there is compression in the top layer, the top layers above the neutral axis contracts, and there is tension in the bottom layer. That means below the neutral axis there is expansion. If we observe the plane EA, it is plane before bending and it is remaining plane after bending also. Now, let's see some practical examples where we can see pure bending case. If we observe the first case, it is nothing but a simply supported beam with clockwise movement and anti-clockwise movement at both supports. Here if we observe, there is no shear force acting at any section of the beam. If we, this is the shear force diagram of this beam. See, there is, because of these two moments, there won't be any reaction force. So, there won't be any shear force acting. Whereas, if we take the bending moment diagram, it looks something like this with magnitude m. That means, in this case, there is only bending moment and there is no shear force. So, this condition is a pure bending condition. And if we take the second example, like in this particular example, there is loading acting at a distance L by 3 from the supports with magnitude P. Here, if we observe the portion AB part, the bending moment is constant with magnitude PL by 3. And there is no shear force acting between A and B. The shear force is 0. So this portion AB is considered to be a pure bending case. Now let's see this condition. Here in this case, if we observe, the bending moment diagram looks something like this, whereas shear force diagram looks something like this. That means at every section of the beam there is both bending moment and shear force acting. That means this is not a pure bending condition. This is an ordinary bending case. Here in this case, if we observe this plane after bending won't remain plane. It deforms something like this. But this deformation is very small and this can be neglected. This particular deformation is due to shear force. So, this plane section remains plane assumption in actual is valid only in the case of pure bending. But as this deformation due to shear is very small, we can assume this assumption in case of ordinary bending also. So, bending stress theory is valid in case of any type of bending. Now, let's see this. Why shear variation is this way. If we observe the shear stress variation in case of rectangular cross section, it is a parabolic one with maximum at the neutral axis and 0 at top and bottom surface. So, the shear stress is maximum at neutral axis. That means the shear strain should be maximum at neutral axis. So, here at neutral axis the strain is maximum, that is phi is phi max. Whereas at top and bottom surfaces, the shear stress is 0, so strain is 0. This is extra information for knowledge. Generally, they won't be asking this in exams. Final conclusion is, the main assumption is in bending stress theory, that is plane section remains plane before and after bending in actual is valid only in case of pure bending condition. But the shear deformations are very less, which can be ignored. So, we can assume this assumption to be valid in case of ordinary bending also. Now, let's see the bending stress variation. Because of this bending moment acting, the bending stress will be generated in longitudinal direction, normal to the cross section, with maximum at the top and bottom surfaces and 0 at neutral axis. This particular variation will be same throughout the cross section. Like if we take any part of the cross section, this variation looks the same. Okay. Here if we observe, the top layer is in compression and bottom layer is in tension. So at the top layer it will be in maximum compression and at bottom layer it will be in maximum tension. Okay. Generally, we will be representing this bending stress variation this way. That is, here we are assuming compression as positive and tension as negative. If we observe, both arrows are towards the section. But the sign convention is positive and negative for both tension and compression. Don't confuse with this and this diagrams. Here in this case, we are taking the tension as away from the cross section and in positive direction, whereas here tension is towards the cross section but in negative direction. This is some sign convention followed. Now let's see the bending stress equation. Bending stress equation is given by m by I equals to E by R equals to sigma by Y. Here m is nothing but bending moment acting, I is nothing but the moment of inertia about the neutral axis. Remember, if we have a rectangular section, if this is the neutral axis of the beam, this is B and this is D, the moment of inertia taken is BD cube by 12, that not DB cube by 12, because bending moment is taken about the neutral axis. Here E is nothing but Young's modulus and R is radius of curvature. After bending, the beam looks something like this in the form of arc of the circle of radius R. Remember, while taking R, we have to take R from center of circle to the neutral plane, not the top or bottom plane. Here, we have to remember one more definition, that is 1 by R. 1 by r is nothing but curvature. In questions generally they will be asking what is radius of curvature or what is curvature. Don't confuse. See the question properly and answer. Here now let's see what is sigma and what is y. We know that stress variation looks something like this. Here sigma is nothing but what is the value of stress at a particular distance y from neutral axis. That is, what is value of stress at a particular plane which is at a distance of y from neutral axis is nothing but sigma. That particular distance is nothing but y. Now we know that this is the bending stress equation. Here this is the extreme condition, like taking stress at the top or bottommost layer, that is y will be y max. This will be sigma max. I assume sigma max is nothing but the strength of the beam, that is Fs. Now taking these two, we will be getting MII equals to F by Y max. Taking I to this side, we will be getting this. Now if we observe this I by Y max, this is nothing but section modulus. Section modulus is given by I by Y max. So now for example, let's see for rectangle case. In case of rectangle, I is given by like about neutral axis, BD cube by 12, and Y max is nothing but distance from neutral axis to topmost layer distance, that is D by 2. So section modulus will be BD square by 6. Similarly, we can calculate for any section like circular section or any section. Now, this particular section modulus is an important concept. In questions generally, they will be asking compare the strengths between two sections. Then we have to compare it section modulus. Section modulus is nothing but it indicates the strength of the beam. More the section modulus, more will be the strength. Now see this. Here M is nothing but F into Z. This is maximum strength of the beam into Z is section modulus. This is nothing but moment carrying capacity of the beam or moment of resistance of the beam. In questions generally they will be asking this also. Compare the moment carrying capacities of the beam. Then we will be comparing the strength of the beam or comparing the section modulus of the beam, and we can obtain the answer. If we see this, it is said that I section is strongest in case of bending. Now let's see how I section is preferred in case of bending. If we observe the section modulus of I section, rectangular section and square section and circular section, I section has maximum section modulus, whereas circular has least section modulus. Now let's see, like without calculating, let's see how we obtain this. If we observe the I section, it looks something like this. If this is the neutral axis, in case of I section, the maximum mass is at farther distance from neutral axis. Okay, see these two are the maximum mass. This is a like thin section, and the maximum mass is at farther distance. We know that moment of inertia is mass into r square, like normal primary definition. So if this maximum mass is concentrating at longer distance from neutral axis, so I will be maximum. We know that section modulus is I by Y max. That as I is more, Z will be more. If we observe the circular section, at the neutral axis, mass concentration is more, whereas farther from the neutral axis, mass concentration is less or decreasing from neutral axis to farther from neutral axis. So, I will be less in this case. So, section modulus will be less in this case. I hope you understood this, like how to compare section modulus. If they ask in exam without calculating, we can compare it this way. Now, let's see if in exam, if they ask which section is preferred in case of bending and which section is preferred in case of shear. For suppose, if they give two sections, one circular section and one I section, and if they ask us like which section is preferred in case of bending and which section is preferred in case of shear, if we see the bending stress equation, it looks something like this. Whereas shear stress variation, it looks something like this. Here in case of bending, we have zero bending stress at neutral axis, whereas maximum at top and bottom surfaces. That means we need maximum material at top and bottom surfaces. So here in case of I section and circular section, the maximum material at top and bottom surfaces is in case of I section. So I section is preferred in case of bending. If we observe the shear variation, it is maximum at neutral axis, whereas 0 at top and bottom surfaces. That means we need maximum material at neutral axis. So in case of circular section, we know that maximum material is at neutral axis and the material goes on decreasing from maximum to least at a surface. So in shear, we generally prefer circular section, whereas in bending, we prefer I section. This is like normal trick or easy way to find which section is preferred in case of bending, which section is preferred in case of shear if they ask in exams. With this, I'll be ending this video. If you find this video useful, please share it with your friends. If you like my content and find it interesting, please don't forget to subscribe to my channel. Thank you for watching.